Greetings. Welcome to our webinar, Latency and Consistency Trade-Offs in Modern Distributed Databases. I'm Andrew Brown, Director of Product Marketing here at ScyllaDB, and today I'm very happy to introduce our guest speaker, Dr. Daniel Abadi. Daniel is the Darnell Canal Professor of Computer Science at the University of Maryland, College Park. His primary area of research is database systems, and his publications have been cited more than 23,000 times. He's known for his contributions to databases of all sorts, from distributed, column store, graph, and stream databases. His best-known contributions include CStore, which was commercialized by Vertica, Calvin, fast distributed transactions for partitioned database systems, and HadoopDB. His work on CStore and HadoopDB won 2 separate Test of Time awards for their enduring impact on academia and industry. Just over 10 years ago, Daniel proposed a new way of thinking about the engineering trade-offs behind building scalable distributed systems. This new model, known as the PACELC theorem, comes closer to explaining the design of NoSQL systems than the well-known CAP theorem. PACELC was formally proved in 2018 in an ACM article. Today, Daniel will provide insight into PACELC, and we'll discuss how ScyllaDB Cloud fits into the latency consistency trade-off to support modern applications with predictable low latency at scale. Questions are encouraged. And please use the Q&A button at the bottom of your screen to ask questions. You can ask at any time during the webinar, and we'll answer as many questions as we can at the end of the presentation. Our agenda today, Daniel will speak to PACELC theorem a little bit over the 10 years since it was formulated, and then we'll take a look at actual benchmarks that we at ScyllaDB performed to quantify this trade-off with a leading database from the NoSQL family. So with that, over to you, Daniel.
Thanks, Andrew. Thank you very much to Scylla and the whole team for inviting me. I'm really excited to talk to everybody today about distributed systems and some of the important trade-offs when it comes to building them and deploying them in practice. So let's jump right in. So every modern database system or data store, whether it's NoSQL, whether it's NoSQL, whether it's regular, traditional, relational database systems, whatever they are, if they're a robust system, they replicate data, right? So you have more than one copy of the data in the system. And there's multiple reasons for this. One reason is just for durability and for robustness, right? So if you have only one copy of the data and that goes away for whatever reason, then you don't have the database anymore, and that's bad, right? So that's one reason why you replicate it. But there are lots of other reasons why as well, right? So when it comes to performance, if you have hundreds of thousands of clients or millions of clients, all hitting a database, right, in this extreme setting, then you need to have more than one sort of copy of the data to be able to serve all these requests coming in from the clients. Furthermore, if those clients are distributed across the world, you want to have copies of the data near where the clients are accessing it, so that we don't get low latency as well. So aside from the normal robustness and availability standpoints of replicating data, you also want to replicate data just for performance, for both throughput and for latency as well. So in practice, that's what we do. We replicate data. So life is all good. We get all these great things about application until things go wrong, right? So one very sort of common sort of theoretical and somewhat practical as well thing that can go wrong is that you can have a situation where the replicas can't talk to each other, right? There's a network partition, or there's some other situation that occurs prevents one replica from being able to send its series of changes to the other replica. If that happens, then we get into a little bit of trouble because now we have a choice to make, right? So if they can't talk to each other, then what do? One option is you simply have one of the databases stay up and running, one of the copies stay up and running, and the clients near that database can access the application. And then the other copy goes down. It's not available because of the fact they can't talk to the other copy. The other one goes down, and all the clients which can only talk to that copy also will see an unavailable database system, and we'll be able to use the application during that period of time. So that's one option, and that's an option which sort of costs you on availability because now half of our users can't use the database anymore. But at least we're not going to get a consistency problem, because the alternative would be, one alternative is that you can allow both databases to stay up and running and serve requests from clients, both read requests and write requests, in which case then you have very good availability because they're both up and running. But the problem is, since they can't speak to each other, any changes that you make will not make it to the other side, to the other copy of the database. So those two copies will diverge from each other, and any read that occurs from one side will not necessarily reflect the writes that occur on the other side. So you have sort of a lack of consistency between replicas, which can cause bugs in the application. If you don't write the application correctly, bugs can occur. So that's another alternative. A third alternative is to simply stay up and running. Everyone can stay up and running for reads and not allow writes at all, right? So you can have full read availability, but we can't allow writes to occur because of the fact that we can't speak to each other. So that's there's these different options, but whatever option that exists, you kind of have to give up either some amount of availability, whether it's just writes, whether it's just reads and writes for half of the database, it's some kind of availability, or you give up consistency, but you can't get them both. And this is basically the CAP theorem. I mean, the CAP theorem is more complicated than that. It sort of says you can choose 2 out of 3 options, but at the end of the day, from a practical perspective, what the CAP theorem really says is that when you have a network partition, you have to choose between either availability and consistency. That's the CAP theorem. But the truth is that the CAP theorem only says you have to choose between consistency and availability only when a partition occurs. So in a situation where we have no partitions, everything is running nice and smoothly, and all the replicas can speak to each other, the CAP theorem would say every system should guarantee both consistency and availability. And so here we are 10 years later than CAP and PACELC and so on. We'll see PACELC soon. And we'd expect to see that every system today, today, by the way, partitions are very rare, right? So they were more common 10 years ago or 20 years ago. Now, to see a global partition across the whole world, it's extremely rare. So given that's the case, we would expect to see every modern system, every new version of a NoSQL system or a new SQL system, every modern system should be both consistent and available, according to the CAP theorem. And of course, that's not what we're seeing. And we see great systems like Scylla, for example, who are sponsoring this webinar, which chooses to give up consistency for reasons other than availability. So the CAP theorem doesn't do a sort of an accurate job of explaining what the trade-offs are today that may cause a system developer or a data store vendor to decide to give up consistency. So to understand that, you need the PACELC theorem, and so let's jump into that in a little more detail. So let's just go with an example here, where we have a truly global application. We're running an application where we have users all over the world, from the US, from Europe, from Asia, Pacific, everywhere we have users for this application, right? So if that's the case, how do you build a data store for that particular application, right? So one option, and the way we used to do things like 10 years ago, 20 years ago, right? What we would do is it wouldn't really be a global application. We would have sort of like a Twitter US and a Twitter Australia and a Twitter Europe, and there'd be separate applications that they have their own separate data stores that they read from, and they can't really read data on the fly, live data from the other versions of the application. Each sort of the application itself is partitioned into pieces that are fully independent from each other. And that makes your life as a data store vendor much easier. You can sort of just provide just a data store which assumes that all users are in one location. That makes life easier, but it reduces the global nature application. So now our users in Australia have nothing really to do with the users in the United States and vice versa. They're all totally separate from each other. And that's not really practical. It's not something we want to do. In our modern applications, we want to have truly global applications where everybody can see the current state of the database of the application in one giant global view of the application. So what do we do, right? So one option is that we could have one copy of our data of the state of this application stored somewhere in the world. Let's just arbitrarily say it's stored in the US, right? So we have our database stored, or our data store, which is storing the state of the application, located in the US. And so if we were to do that, then what would happen is that we would have really great performance for those users in the US who are using our application they would see amazing performance because they're basically seeing local data, especially let's say if the database is in the Boston area, is physically stored, data is physically in the Boston area, and all of our Boston users will see excellent performance. You're talking about 10 milliseconds round trip from the client to the data store and back to see the current state of the application. We're talking in the order of 10 milliseconds. That's great. The problem is that everybody else is going to see very slow performance, right? So if you're located in Australia or Asia or any other location in the world besides the US or northeast of the US, if the data is in Boston, you're going to see some increased delay to go back and forth to see what the current state is of the application. Right, so if you only have one copy of the data and it's in one location, then what you're doing is you're sort of allowing some users to get fast access and everybody else gets slow access. Plus, you have this other problem, which is that you have this sort of lack of availability. If that region goes down for some reason, if something happens to the Boston area, then that's it. Then the whole application is down. Right. So you have two major problems if you don't replicate. So another option is you could replicate data, right? So one very common way to do replication is that when any system across any user client across the world, when they try well, let me back up a second. So what we'll do first, we'll replicate data everywhere, right? So we'll have one copy of the database in the United States, one copy in Australia, one copy in Europe, one copy in Asia. We'll have one copy of our state of the application wherever we have users, right? So therefore, every user, when they want to read the current state of the application, they're going to see fast performance, right? So they'll go ahead and they'll send their query, their request to see the state to their local copy of the application state, and they'll get back the response back like everybody, like before our Boston users. Now everybody will see that same performance of 10 milliseconds to respond back to a request to read the state. So that's great. If we have copies everywhere, we're going to see really fast read performance in general. The problem is, what happens if you do it right? So now, if let's say we have a user in Australia who wants to write to the database, what's going to happen, right? So if they write just to Australia and nowhere else, then the write will occur quickly. But the problem is then you won't see that write in Boston immediately. There'll be some delay before the write makes it to Boston. Right, so we can have a write occur in Australia, and then a read occur in Boston right afterwards, and that read in Boston will not see that write that occurred in Australia, right? So that would be sort of a way to get sort of a low latency write, but unfortunately that would cause a consistency problem. Alternatively, we could do what's shown on this slide here, where we would replicate those writes before we commit the write to the data store. In other words, before we tell the client the write's done, what we'll do is we'll take this write that occurred in Australia, we'll replicate it all the way to Boston, and then once it makes it to Boston and we know it's there, then at that point we can tell the client that the write has occurred, and that will guarantee that any future read that occurs after the write is done will reflect the state of the data store after the write occurred. So this is what's done in many systems today, right? So for example, Spanner, Cockroach, many other systems, including ones from like Calvin and Slog. They all do things in this way, where we have some sort of consensus that gets reached on writes to ensure that every copy of the store across the world agrees on what the writes occurred, or at least the majority of copies. So there's a whole consensus usually works in the majority protocol. It's a little bit of a separate question there, how that works exactly. But roughly speaking, all or a majority of copies see the write before commit, and then any subsequent reads see those writes with high consistency, and the reads themselves can be fast, right? So basically what happens is at the end of the day, writes are slow and reads are fast if you do it this way. There is sort of a little bit of a change of this. You can make reads slow and writes fast. You can have writes just go to the local copy, and then reads have to go everywhere to make sure we see all the most recent copy of everything. That's a little bit more rare in practice. I'm not going to talk about it so much. In practice, what you usually see is you see reads be fast and writes be slow in these sort of high consistent systems like Spanner and Cockroach. So that's one option. But again, it's still kind of, if you have a truly global application, we actually have users in Australia and the United States, 400 milliseconds for a write is just too slow. It's just not really acceptable to have writes take that long in practice. If you have users sitting at a web page or at the application, and they have to wait, at least 40 milliseconds for write to go through, they see that performance, and that reduces the user experience. So you often see sort of a variation on this theme, where instead of having all of the users see slow writes. Instead, what we'll do is, since most reads and writes to data come from a particular location more often than other locations, for example, let's say we have, we're a social network and we have users in the US and we have users in Australia and so on. So, probably the users that are located in the US are the state associated with the users are most often accessed in the US. Similarly, those users located in Australia, the state of those users are going to be accessed more often in Australia. So you have a natural sort of geographic partitioning of the application access in the way that users interact with the data store. If you have that, you can play some tricks here. You can do things like, while still guaranteeing consistency, you could sort of geographically partition the data such that data is physically located in a region where it's most often accessed. And if you do it that way, then it's possible to do things like have both reads and writes that local data be fast. However, if you ever want to see data in a remote location, right? So if you happen to be a US user and you want to see an Australian user data, then both the read and the write to that data will be slow. So either way, you kind of get either way you get consistency. Whether you go where you have the previous slide, where it's just a simple consensus protocol, or you have this more geographically partitioned consensus protocol. Either way, you get consistency. You can get strong consistency, but you pay latency some way, right? Either you pay latency because of the fact that in the first slide, because all writes were slow, or only reads and writes to remote data are slow. Either way, you have to pay some latency cost to get that high consistency. That's one sort of way you can go about doing things. Another way you can go about doing things is you can say, let's just sort of reduce our consistency a little bit and get some better performance that way, right? So what you can do is you can allow each user, like we were talking a little bit before, the Boston users can interact with Boston data, and the Australian users can interact with Australian data, and they can even interact with Boston data as well. And if they do, then I'll still write it to the local version of the database, right? So a Boston user that writes Australian data, they'll have a copy of Australian data in Boston, and they'll go ahead and they'll write to that Australian data in Boston, and they won't immediately make it to Australia. So it's possible that our Boston user will edit Australian data in their local version in their local replica. And then the Australian user will at the same time edit that same data item in Australia or read it. And they won't see the effects of that write that occurred in Boston, right? So in that situation, then the replicas temporarily diverge because of these two concurrent writes occurring in different locations. And you have to have some kind of protocol after this divergence to sort of allow the replicas to come back in sync with each other, right? So you have to have some after the fact resolution protocol to ensure the replicas eventually agree on what occurred. So if you do that, then it's a little more complicated for an application developer to sort of be able to handle this sort of these conflict resolution protocols to ensure that that we are able to get back to one state after these conflicting edits. But what you get though is you get latency. Right? Now all reads and writes all fast. They all are dealing with local data, and as long as we have some way in the application to handle these potential for conflicting states due to lack of consistency, then we can get very low latency on both reads and writes. So at the end of the day here, what's hopefully very clear at this point is that you have a trade-off between latency and consistency, right? So in the first two options we saw, the regular consensus or the partition consensus options, you get consistency, but you pay latency in some way. Or you get latency, but then you have to pay consistency in some way, right? It's a fundamental trade-off that you can't really get around, and it has nothing to do with availability, right? In this situation over here, we have two replicas choosing to diverge from each other, even though they can communicate. There's no network partition here. There's no reason why they can't communicate. They just choose not to because it's just too slow. So there's just a fundamental latency versus consistency trade-off that occurs when you're dealing with geographically dispersed deployments in a distributed system. So that's what leads us to PACELC and the PACELC theorem. And just to quickly review it here, what the PACELC theorem says is that sort of two major reasons why you may want to give up consistency, and they're different from each other. You may want to give up consistency because of the fact that you may have a partition, right? If you have a network partition, this is the CAP theorem basically. If you have a network partition, you may want to give up consistency to get availability. But even if there are no network partitions and everything is operating normally, you may still want to give up consistency in order to get latency, right? So basically PACELC says the P of PACELC is if there's a partition, then what do you choose? You choose the A or do you choose the C? If you want to choose availability, consistency, that's the CAP theorem. Else, if everything's operating normally and there are no network partitions, then what do you want to choose? Do you want to choose latency or do you want to choose consistency? There's a fundamental trade-off that you can't get around it, and it was formally proven by a different group. And you have to choose, and you have to decide how to build your system. And in practice, you see sort of a whole different category of you have many different modern data stores for distributed applications, and they choose different points in this PACELC space. For example, you can sort of say if there's a partition, you can choose A, you can choose availability. And if there's no partition, you can still choose L over C, right? So in other words, we're going to give up consistency both on the partition and on the no partitions, and we get both high availability in the partitions, and we also get very good low latency performance by giving up some consistency at runtime, even without partitions as well. So those PAEL systems, there are lots of them. Dynamo, Cassandra from the previous generation, and the modern and Scylla is a good example of a modern version of a PAEL system. But either way, what they all do, all these types of systems, they all choose to give consistency both on the network partitions, but also even if there's not partition, just to get better performance. Those would be PAEL systems. I think Andrew can talk a little bit about, Scylla also has a version with high consistency if you want it. It's coming out pretty soon, so I'll let Andrew talk about that. Alternatively, you could say, no, I want to build my system to really guarantee consistency all the way through, right? So no matter what, whether there's a partition or no partition, either way, I want to ensure that all my data is fully consistent with each other. All my replicas fully agree with each other, that there's no sort of visible divergence of my state in my application across all my replicas. That's also a very common approach. There's lots of applications which prefer this type of guarantee from the data store. And therefore, there exist PCEC data stores which guarantee high consistency under all scenarios. Right? Examples of this would be Spanner, Cockroach, Calvin, and Slog, and so on. There's lots of examples of both all these categories. Alternatively, you could say, let's choose the PAEC space in PACELC, right? So we're going to say that normally we're going to operate on high consistency, right? So we choose consistency over latency under the normal setting with no partitions. However, availability is paramount. We can never allow application to go down. So if a partition does occur, only at that point do we give out consistency, right? So that would be a PAEC system where we're under normal application, we are highly consistent, but if things go wrong, only when things go wrong do we give out consistency to get availability. That's another option. Those options exist as well. PCEL is a little bit rare. There's no really good reason for it to exist, right? If you're going to be if you're going to optimize for latency and give up consistency on the normal operation, there's no really good reason why you wouldn't give up consistency also under a partition as well. So I don't really know any good examples of PCEL system that really operate that way in practice. I mean, in theory, they could exist. I just don't know of any practical examples. So I think I'll stop for now. I think we're getting a little short on time here. So I'll let Andrew take over now, talk about Scylla a little bit. And then I'm happy to answer questions about any of this during the question and answer period at the end of the webinar.
Right, great. Thanks a lot for that, Daniel. In light of the PACELC theorem, the question that we asked is, can you put a number on these trade-offs that Daniel's been discussing? So last year, we decided to put together a benchmark that might answer that question. We wanted to compare ScyllaDB with another next generation distributed database, but one that favors consistency over latency. And we chose CockroachDB for the comparison. As Daniel touched on, CockroachDB is an open source alternative to Google's implementation of the Spanner protocol. It's able to run on commodity hardware as it uses those similar algorithms and techniques to provide distributed transactions like those of Spanner. And as a next generation distributed relational database, its primary focus is consistency, along with flexibility and support for structured query language. It provides high availability the same way Scylla does through data replication, but it maintains consistency across replicas while serving concurrent transactions. And as Daniel pointed out, maintaining consistency inevitably imposes additional overhead. So CockroachDB uses a number of techniques to mitigate that overhead of consistency and to provide high performance quality of service in many cases. So for example, one example is a hybrid transaction scheduler that makes reads linearization cost-free. CockroachDB is written in Go, so it's susceptible to garbage collection spikes. As Daniel mentioned, in PACELC terms, CockroachDB is PCEC. Scylla, in contrast, is PAEL. It focuses on extracting every drop of available CPU and networking power to minimize latency. The trade-off, of course, is consistency. Like other NoSQL databases, ScyllaDB provides what's known as eventual consistency by default, though it also offers a stronger API, an API for stronger consistency that leverages lightweight transactions. And it's noteworthy that the latest version of Scylla, Scylla 5, will include RAF support, which will provide a stronger type of consistency that is sometimes referred to as immediate consistency. Even then, a comparison with a distributed relational database like CockroachDB will still be apples to apples. Sorry, apples to oranges. What ScyllaDB does not provide from an ACID perspective is isolation. And isolation is required by applications that perform the types of transactions, multi-statement, cross-partition transactions that CockroachDB was built to service. Again, we want to be very clear, this is not a competitive benchmark. It's an apples to oranges comparison. ScyllaDB and CockroachDB are built for and used for very different use cases. We did this mainly out of curiosity and an interest in quantifying latency and consistency trade-offs. So for the comparison, we ran a series of benchmarks defined in the Yahoo Cloud Serving Benchmark Test Suite, which of course is a widely used industry standard benchmarking framework that measures scalability and performance, defined as latency. The benchmarks run on identical setups, 3-node clusters in a single region across 3 availability zones on i34X large instances, and software versions used were Scylla 4.2 and CockroachDB 21.6. So here are the results. Initially, we aimed to populate both databases with a data set of 1 billion keys, but loading issues kind of forced us to reduce the data set size for CockroachDB to 100 million keys, and ultimately just over 1 terabyte of data, which was later compacted to 450 gigabytes. ScyllaDB, in contrast, easily loaded 1 billion keys and ran the benchmarks against almost 5 terabytes of data. For the 1 billion key data set, ScyllaDB managed to serve 150,000 to 200,000 operations per second on most of the workloads. And on average, ScyllaDB achieved 180,000 operations per second with P99 latencies under 5.5 milliseconds at 75% load. And even with a smaller data set of 100 million keys, CockroachDB ran up against some performance and scalability limits much earlier than ScyllaDB, as you can see in the results chart. So for workload A, which is update heavy, basically 50-50 read-write ratio, CockroachDB recorded 16,000 operations per second with P99 under 52 milliseconds, and with workload D, Cockroach achieved its best result with 40,000 operations per second and P99 below 176 milliseconds while running at about 80% CPU utilization. Notably, increasing the load didn't increase throughput with Cockroach. Instead, the higher load simply increased the latency. So to summarize the results, loading 10x the data into Scylla took less than half the time it took for CockroachDB to load the smaller data set. Scylla handled 10x the amount of data, and Scylla achieved 9.3 times the throughput of CockroachDB at 1/4 the latency. You can find the complete benchmark results at this URL, along with benchmarks for a number of other well-known databases. Additionally, we have a white paper on the subject that goes into more detail. So this brings us to ScyllaDB Cloud. ScyllaDB Cloud is a distributed non-relational DBaaS for distributed applications that require high availability, predictable low latency, in contrast to the workloads characterized for CockroachDB, which are characterized by modest database size, which require strong consistency guarantees and transactions along with a relational database model, especially those involving joins. But ScyllaDB Cloud gives you these performance benefits on either AWS or Google Cloud, with the added benefit that our database experts become essentially your DevOps DBAs. And of course, these days it's hard to find talent to run a distributed database. It's a challenge and it's very expensive, but ScyllaDB Cloud lets you focus on your business and your applications rather than tuning and babysitting your database. And especially among our customers who are modernizing from legacy NoSQL, we're seeing really strong results. And one great example is Comcast, who are able to reduce their latencies by 95% by moving from Cassandra. And they also went from 962 Cassandra nodes to only 78 nodes of ScyllaDB, so much lower operational overhead and big cost savings, around 60%. And just to show you how obsessed we are with our position in the PACELC theorem, we sponsor an annual conference called the P99 conference. It's an event by developers for developers, and you can visit p99conf.io to view last year's presentations and also to submit a proposal to speak at this year's conference in October if low latency and P99 measurements are of interest to you. So with that, I think we'll go ahead and move over to the question and answer portion. We've got a few questions coming in here. And the first one, Daniel, is from Srinath Suresh, who's asking, how do the resolution protocols work in case the same data has been modified?
Sorry, that was on mute there. It's a very good question. So different systems do it in different ways, and many systems actually allow the application to determine that. The most common resolution protocol is just last write wins. So if you have two conflicting writes, the same data item, whichever wrote last is the one that wins. So that's very dangerous when, for some applications where overwriting data and sort of pretending as if the first write never existed can be a problem. And so what you end up having to do is you end up having to sort of write the application in a way that that each write itself is sort of its independent entity, and sort of not seeing previous writes because they got overwritten because of the last write wins rule doesn't end up mattering. So it is a little bit trickier to write into applications, and there are alternatives, right? So you can also have sort of a user-defined conflict resolution protocol that does more advanced things when it'll sort of see the different writes that occurred, and then based on application logic, sort of develop some new version of the data which sort of incorporates both those writes into this new value of the data item. So it can get complicated and non-trivial, and that's why PCEC systems exist, right? So some applications prefer to write data over a database which guarantees consistency for that reason, because it can get complicated. But if you're willing to pay the extra sort of complication at the application level, you can get much better performance by not forcing the database system to guarantee consistency. So that's why they both exist. There's a good room, there's plenty of space for the PAEL systems to exist. There's a lot of space for the PCEC system to exist as well. We need them both in practice for different types of applications.
That's great. Here's a good one. Can you talk a little bit about PACELC in a distributed setting versus PACELC on a small cluster in a single region?
Sure. Yeah. So yeah, I noticed in the benchmark that you presented, sort of it appears like there wasn't sort of a truly global setup. It seems like it was mostly in a local cluster, and you were still seeing sort of some pretty specific performance differences between Cockroach and Scylla. So So that would so let's back up for a second first. So at a theoretical level, before we get into actual practice, right? So at a theoretical level, the PACELC theorem is more I guess impacts the design of the system more when you have a fully geographic replicated data, right? When you have a deployment where you have data in the US, data in Europe, data in Asia, a fully geographically diverse deployment, then you really have to pay attention to the PACELC theorem, because the trade-off between latency and consistency is very, very large, right? So you have these sort of like half a second delays to get anything done. Once if you do have consensus across the whole world, it's very, very slow. Now, if you're in a local cluster, the consensus goes faster, right? You can get that consensus done in say 20 milliseconds or so, even less than that sometimes. So the cost of the latency kind of goes down as you get more narrow in the deployment, but it still exists, right? So when you're dealing with sort of the type of performance that Scylla like to talk about, where Scylla's gone and sort of they optimized every last every last bit of the database system to everything's really super optimized. So then when you get to paying even the 20 milliseconds to communicate with the local cluster to get that consensus done is still very expensive. So the PACELC theorem exists in both places. Like PACELC is really, really important at global distribution, but even at a local cluster too, PACELC matters. You have to be aware of it. Even a local cluster, you can get if you really want to get a fully super low latency system, you have to pay attention to PACELC also in a local cluster as well, like you showed. I would say also that I would guess, just looking at your results, I should just say I wasn't all involved in the benchmark. I don't know anything about it besides what you presented, but I would say that my guess, looking at your results, is that not all the difference can be attributed to just the consistency latency trade-off. It's probably some other factors there as well, including like ones you mentioned, like the activity in C++ and there's no garbage collection. All those things probably makes a difference as well. I mean, there's also other things. For example, whenever one company benchmarks against another company, sort of, they don't know the other database so well, so it's a little harder to get everything set up. So, there's, there are many factors there. So in an academic paper, you'd have to sort of break it all down about why the performance exists. In an industry benchmark, you don't have the same level of peer review to ensure that everything is explained fully academically rigorously. But my guess is from those results, there's a combination of PACELC there, combination of C++ and no garbage collection, and maybe some other factors there as well.
Mm-hmm. Yeah, that's great. Great point. We got one question that's specific to Spanner, which is interesting. Cockroach does not guarantee as strong a consistency as Spanner, upon which it's based. Would the PACELC theorem therefore say that Cockroach gets better latency than Spanner?
That's a great question. That's a really sort of insightful and deep question. So really, we could do a whole webinar on that topic just by itself. I'll try and spend a few minutes now talking about it a little bit. So Spanner guarantees what's called eventual consistency. Not eventual, external consistency, which is sort of the gold standard, the highest possible consistency possible. Spanner guarantees. In other words, every single write that occurs is guaranteed to be seen by any future read. If once we tell the client the write's done, it's there. It's going to be seen by any future read. There's no way around that. It's just 100% fully excellently consistent. There's no way for two reads, if no write occurred, for two reads to see a different value. It's like it's one copy. Even though it's replicated everywhere, it's as if it's one copy. It's a beautiful, very high consistency guarantee. Cockroach is not quite the same level. It's very close. So for the vast majority of applications, you will see in Cockroach almost the same level of consistency as Spanner. It's very hard to see a difference, but there is a sort of a very narrow corner that exists in Cockroach for which you would see a consistency violation that you wouldn't see in Spanner. And what that is this thing called the causal reverse. What could happen is the following. You could have one write come in. So a user one writes something else. Actually, you know what? Let's do an example. I think we have time. So let me just sort of give you a real example. Let's say we're a bank and want to transfer money we have a customer, we have a client that wants to transfer money between two of his accounts at that same bank, right? So they have, let's say, a checking account, they have a savings account. That's a typical example. I heard now nobody has a savings account anymore, but whatever. Let's assume we still have savings accounts in the real world. And we have they have a checking and savings account, right? And they want to transfer money between the checking account and the savings account. And the way that works, and the way most banks work, there's not one transaction. You don't sort of move it over in one sort of atomic unit, but rather what happens is the money goes out from the checking account into some sort of a bank-owned account, maybe in a different database system, and then it comes back out from the other account back into the savings account. It's sort of like a two-step process. And so therefore you have sort of two separate transactions which occur. You have one transaction which reads the old value of the checking account and subtracts some amount from it because you took it out of the checking account. So it subtracts money from it. And then you have a separate transaction later on, which is caused by the first transaction, because the second one would never happen if the first one didn't exist. But after the first transaction completes, you have a separate transaction which occurs, which moves the money from the bank-owned account back into the savings account, right? So sort of, temporarily speaking, you have sort of the customer has, let's say $10,000 in the checking account, and it goes down to zero temporarily, and then back, to $10,000 in the savings account when the second transaction goes through. But those are issued as two separate transactions, and they're touching two different data items. Now in Cockroach, if the bank-owned account is stored, if it's located in an external database somewhere else, not in the original database, then what can happen is if I had a transaction which wanted to read the sum of the checking account and the savings account, it's possible that you could see a situation where you see the value of the savings account after the money went back into it, i.e. $10,000 into it. And you also see the value of the checking account before anything happened was still $10,000. So even though the customer had a total $10,000, which they transfer from checking to savings, and each one was zero before the transfer, it's possible that the read will see the value, like sort of they'll reverse the order of the causal relationship between the checking account decrease and the savings account increase. They'll have this causal reverse where they'll see the value of the savings account after the transfer, but the checking account before the transfer, and therefore have this anomaly where they see this customer has $20,000 temporarily, even though they never had $20,000 in their life, right? And the reason why this is possible is because Cockroach doesn't do this thing called a commit wait, right? So in Spanner, so Cockroach is based in Spanner, as you mentioned, Andrew, in your slides. But in Spanner, what happens is whenever they do a transaction, they have this this commit wait which occurs to ensure that even though each clock and each machine involved in that transaction may be a little bit different from each other, but there's some maximum bound that could be. Like it could be that we sort of assume that no two machines are more than, say, 10 milliseconds apart from each other. Every clock is within 10 milliseconds bound every other clock across the whole deployment of our Spanner cluster. So then Spanner will wait that extra 10 milliseconds at the end of a transaction to ensure that the timestamp we give to this write will never be sort of exceeded by a future write that comes along afterwards, because we've sort of enforced that any future write that comes afterwards will get a later timestamp because we waited this commit wait amount of time to ensure that this maximum bound of differences of clocks will pass in Spanner. Cockroach does not wait that commit wait. They don't have this commit wait except for certain types of transactions, but the average transaction does not have this commit wait. So they get latency benefits by not having this commit wait, because they don't have to wait this, this time bound extra 10 milliseconds or so for each transaction. But as a result, they are susceptible to the causal reverse. So at the end of the day, therefore, you have like the PACELC theorem appearing again, even within this trade-off, even between Spanner and Cockroach, which are themselves, they're both consistent systems, but Cockroach gave up a little bit of consistency and they got a little bit of extra latency, right? They paid a very small amount of consistency to get down to this, to get this causal reverse, which happens very rarely. So it's a very small consistency decrease, but then they got this very small latency increase where they don't have to pay that extra 10 milliseconds or so for that commit wait per transaction. So, and this actually sort of has a big implication on the PACELC theorem overall, right? Which this would indicate that it's not all or nothing, right? It's not like PACELC, when we say that, ELC of PACELC, it's a latency versus consistency trade-off, it's not really L versus C, like either you get latency or get consistency for only one of them. It's sort of every small little bit of consistency you give up, you have to pay some latency. So it's sort of like it's a range, right? So you get a little, so you can have a full consistency, you can have a little bit less than that, and you can have a little bit of latency benefit as a result. So it's sort of it's a range that exists even within the ELC of PACELC this question really brings out in understanding sort of what happens when you go from span to cockroach as far as consistency goes.
Very interesting. So I think another way of putting that might be that there are trade-offs within trade-offs within trade-offs.
Yeah, I guess so. Or you could just sort of say it's a spectrum, right? Sort of like, consistency is not, it's not that you're either consistent or not consistent. It's sort of like there is full external consistency, there is strict citability, there is serial consistency, there is call consistency. There's also sort of different sort of points on that consistency range which exists. And each one, the more consistency you get, the more you get towards one side of strong consistency, the more latency you have to give up. And so it's really sort of a very interesting trade-off there in the ELC of PACELC.
So here's a good one. Do you see the tension in these trade-offs? Do you foresee it getting worse in the future as systems become more distributed?
Yeah, I think so. I mean, like, yeah, so as we were saying before, the PACELC hits you harder the more geographically dispersed you are. And so what we're seeing in modern times, especially 10 years later after the original, sort of CAP and PACELC theorems came out, is that we're much more global as a society now than we ever were, right? So we're really sort of dropping all kinds of barriers, and we're seeing applications from the beginning to be expected to be fully global across users everywhere. And PACELC really gets you when you're really fully geographically dispersed. You have to have some way to handle that latency consistency trade-off. You have to think about it very hard about what you want to give up, and you really have to give something up. There's no way around it. So it's getting more extreme as we become more global as a human society.
Indeed. Well, that's all the questions we have for today. So I think we can go ahead and wrap it up. Thank you very much for joining us today, Daniel. I think everybody enjoyed it, and it's been a great discussion, and we're looking forward to talking with you again in the future. Everybody joining the webinar, thank you for joining. We'll be providing the slides online at a future time, and we'll email you about that, and a recording will be available as well. So again, thank you everybody for joining, and we look forward to continuing the conversation.